Every point in the Mandelbrot set is defined by the behavior of 0 under repeated iteration of the function z squared plus c. If the resulting sequence stays near the origin forever, the complex number c is a member of the set. If the sequence escapes to infinity, it is not. A fundamental theorem in complex dynamics states that if the absolute value of any iterate exceeds 2, the sequence will definitely diverge to infinity. This escape radius of 2 provides the hard boundary used by all computational algorithms to visualize the fractal structure. Unlike Julia sets, which exist in the dynamical z-plane, the Mandelbrot set lives in the parameter plane. Each pixel represents a unique value of c, making the set a map of all possible behaviors for the quadratic family of functions.
The largest central feature is the main cardioid. For every value of c within this region, the iteration of 0 converges toward a single stable fixed point. This is the region of period 1 stability, where the system reaches an equilibrium. Attached to the cardioid are circular bulbs. When c enters the largest bulb on the left, the orbit no longer settles on one point, but oscillates between two distinct values. This marks the first step in a period doubling cascade toward chaos. Each bulb has a specific period associated with it. The period of a bulb is determined by the denominator of the rotation number of the internal rays. This creates a highly ordered mathematical structure governed by rational fractions.
The boundary of the set is where the most interesting dynamics occur. It is a fractal curve with a Hausdorff dimension of exactly 2, meaning it is so convoluted that it effectively fills a two-dimensional area despite being a boundary. Gaston Julia and Pierre Fatou proved that the Julia set for a specific value of c is connected if and only if c belongs to the Mandelbrot set. This makes the Mandelbrot set the index of all connected quadratic Julia sets. Misiurewicz places are specific locations on the boundary where the orbit of 0 is pre-periodic but not periodic. At these points, the Mandelbrot set looks locally similar to the Julia set for that same value of c.
We can analyze the exterior of the set using conformal mapping to the unit disk. External rays are lines perpendicular to the level sets of the potential function. They provide a coordinate system to navigate the fractal wilderness. Deep within the filaments, small replicas of the entire Mandelbrot set appear. These mini Mandelbrots are not identical copies, but are slightly distorted by their local environment, illustrating the concept of nonlinear self-similarity. To render these sets efficiently at high zoom, we use the distance estimation formula. By calculating the derivative of the iteration, we can estimate how far a point is from the boundary, allowing for smooth, sub-pixel accurate details. One of the most famous open problems is whether the Mandelbrot set is locally connected. This property would imply that the set can be described entirely by its internal and external rays, bridging the gap between topology and dynamics. Moving along the real axis toward -2 reveals the pathway to chaos found in the logistic map. The points where bulbs meet represent bifurcations, where the system's stability splits, eventually leading to a dense region of chaotic orbits. Modern exploration of the Mandelbrot set requires arbitrary precision arithmetic. At zooms of 10 to the power of 100, standard 64-bit floating point numbers fail, requiring specialized software to maintain the integrity of the math.
Determining the exact area of the Mandelbrot set is an ongoing challenge. While Monte Carlo simulations provide an estimate around 1.506, a closed-form expression remains unknown to this day. The interior of the Mandelbrot set consists of hyperbolic components. In these regions, every point C has an attracting periodic cycle. It is conjectured that these components are dense in the set, meaning any non-hyperbolic point is a boundary point. The Mandelbrot set is not just a pretty picture, it is a universal map of complexity. It appears in various branches of science, from fluid dynamics to electronics, wherever a simple non-linear feedback loop is present in a complex system.